We're going to do a demonstration this morning. Hector, you feel like filming another demo? Okay. It'll be in about 10, 15 minutes. We get a little bit of instruction first. We're going to finish off with a little bit of thermal mixing, and then talk about standing waves and the general topic of interference. And then we'll close class today with a small discussion of the phenomenon called beats, which is how traffic police nab you. Now, this is the first lecture of April, so we have a new quote of the day, individual Benjamin Franklin. And one of the things that if he were here today, he would be asking this question: Are there any, are there any SSG spots left? And of course, I'm ready for him because the answer to that is yes. Here's what we've got right now, as of a few minutes ago. Raymond Ordonez, Michaela Hermano, Maria Spinetti, Caitlin Widener, and John Eisner. I believe everybody else is full. Okay, so those are all Tuesdays. And what we're going to do at the end of lecture, hopefully if we have some extra time, we'll actually get those guys up to the front. And all you SSG leaders, if you haven't gotten your attendance sheet from me, Caroline's got them up in front. Pick it up right after class or when we dismiss. But if you haven't snagged a Tuesday spot, there's still a few. Let's see, John's got 5, Caitlin's got 3, Maria's got 3, Michaela's got 1, and Raymond has got 1. All right, so, and I wish everyone great success with that. Now, let me go back to the regular display. If I seem a little bit cranky this morning or a little bit out of it, it's because I was staying up really late, watching and getting yelled at by my wife for staying up so late, my son and I watching this game and totally having heart attacks. But that was a sweet shot at the buzzer. I tell you what, that was really nice. All right, now, I want to talk about the SSG study schedule just a little bit more. It's the sign-ups page. For most of you, you went through the sign-up link. Good. Try to get in there. Now, you can go in there now if you want and sign up quickly. And all you got to do is click on the group. And if it's full, it's full. It won't let you click. But if it is, got some spots, then you're good. All right, mixing. I want to talk about a fairly simple example. Go ahead and write this down. This is our beginning notes. We'll have a clicker question on this in just a few minutes. And I may give you a mixing problem of some degree of difficulty on the exam, either on midterm exam 3, maybe on the final. And don't forget, the final exam, which everyone here currently is obligated to attend and take part in, except for the SSG leaders, maybe if they do all their tasks. The final exam is cumulative. And so I can ask you any kind of question, William DeClerc, from day 1 through end of May or end of April. And as I always say, to get ready for my exams, study everything and expect the unexpected. All right, so we have 2 substances, substance H, substance S. They're not at thermal equilibrium, and so I've drawn them as 2 blobs, one yellow, one blue, and I've spec'd out the temperatures for substance H, 333 Kelvin, for substance S, 288. And there's nothing special about these temperatures, just some that I dreamed up. Okay, now each is a different substance, and so we'll assume they're liquids. And because they're different, that means gram for gram, Kelvin for Kelvin, they're going to have different degrees of heat up ability. In other words, the specific heats are going to be different. And because that is true, the same number of calories gained or lost by either liquid is going to lead to different temperature changes. When you mix them, the cold into the hot, the cold is going to warm up. The hot is going to cool down. Even if they don't really mix, if they're just in thermal contact, like two pieces of metal, they'll eventually come to equilibrium temperature, even if they don't really mix. But we'll assume they're like two different liquids and they're going to mix and stuff the way substances do. Each substance also has a different mass, and the mass specification that I dreamed up for this simple example is 40 grams for substance H and 75 grams for substance S. And when you were working on the homework over the weekend I think last week maybe, the candles, those were paraffin wax, and they had a different specific heat than water. Solid paraffin wax was different from liquid paraffin wax, just as solid H2O is different specific heat-wise from liquid H2O and gaseous H2O. So because they each have a different amount of mass, this is another reason that exchanging heat from hot to cold will lead to different temperature changes, calorie by calorie. And because energy is conserved, we're going to assume this is in a really nice thermos container, so no external energy. The only thing that's going to redistribute is the existing energy in each liquid. And therefore, what one loses, the other one gains. So substance H is going to lose some calories, but they're not going to go missing. They're simply going to be going into substance S. So what substance H loses, substance S will gain. Make a note of that. That's a basic application of the conservation of energy. And this is including thermal energy now, not just mechanical energy. So here's the thing that we would want to figure out. For instance, if substance H cools down, it loses 1 calorie. So Q subscript H is negative 1 calorie. That's going to be 40 grams times 1.2 calories per grams times some delta T. Now, to figure out the equilibrium temperature, you've got to figure out this dip. Delta T subscript H is going to be negatory, Raymond. And because that is the case, you have to calculate it very carefully, and you have to use this minus sign right here where it says Q subscript H, Alexandria, is minus 1. Yeah, we're going to keep that minus 1. Now, heretofore, we've been heating things up. So all our Q's have been positive because we're adding heat to heat stuff up. But this is mixing, so one thing is cooling off and another thing is heating up. The thing that cools off is dropping calories. So let's drop 1. Let's drop 1 calorie and then calculate the dip in the temperature of substance H. Now, here's your basic information again, and I've got 4 multiple choice options for you, and what you've got to do is figure out for minus 1 calorie, you've got to execute MC delta T and figure out, well, not execute it, but work with MC delta T equals minus 1 calorie and figure out what delta T is. Under the assumption that specific heat is 1.2 and the mass is 40. Go ahead and calculate. The correct answer is up there, and there's some tempting answers, and as you know, you have to have a correct answer on a multiple choice, right? But you also have to have um, something that's tempting. Oh, it's not even open. Let me start. Sorry, thank you. All right. Okay, you can start voting now. And what we're going to do, my wonderful students, we'll go through the calculation here in case you get tripped up. And I'll probably give you some homework on this topic to work on tonight. It's cooling off. Cooling off, right? Substance H cools off, yeah. So delta T, if you know nothing else, what is delta T? Yeah, it's a change, but even if you don't know the number, what can you say about what? Negatory, yeah. Right? Cool off means delta T is negative, yes. 30 seconds. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Bring your clickers to class on Thursday for the exam. Wow, you guys are, well, let's see. These are the answers. A lot of you voted for B. Let's check it. Here we go. Um, Here's your formula that you're working with. Q equals mc delta T. Now, previous to this, we've been trying to figure out Q, given a mass, a substance, and a delta T. This time, we're trying to figure out delta T on the right here. And this is the amount of heat that we're working with, an exchange of 1 calorie. So these two substances are going to be trading calories of energy, basically. Hot to cold, okay? You know, cold's going to gain 1, hot's going to, substance H is going to lose 1. All right, this is losing 1 calorie. There's 40 grams of the substance. The specific heat is 1.2. So if you cancel out grams and kelvins, no, grams and calories, calories left and right, grams on the right, top and bottom, you're left with per Kelvin in the denominator over here. Here's solving. Now these two parentheses over here on the right, 40 times 1.2, that's 48, okay? And I divide by 48 on both sides, and it's actually, Amber, 48 per Kelvin, okay? And so the quotient here works out to, let me check something here, negative 0.0208. And students, I see that 76% of you did get that. Some of you voted for D. Now, D is the inverse of that. So if you voted for D, you forgot to go 1 divided by 48, negative 1 divided by 48. All right? Now, go ahead and jot down this calculation. And let me close this. And so delta T for this first calorie is negative 0.0208 for substance H. Now, you're going to get a different delta T for substance S, but you calculate it the same way. You put a plus 1 calorie and an MC delta T using the mass of substance S and the mass of, or the specific heat of substance S. Here they are, over here. And that's going to get a little bit hotter. It's going to have, so the new temperature after exchanging 1 calorie with substance S, substance H has a little bit less, 332.97917 Kelvin. All right, so in general, you can figure out, calorie by calorie, what each new temperature is. Okay, so we could use the same strategy and get the new slightly higher temperature for substance S. And when the two temperatures are the same, then you've reached thermal equilibrium. And so theoretically, you can figure out thermal equilibrium by using exchange of 1 calorie or maybe exchange of 1,000 calories. This one's probably better to, instead of using 1 and minus 1 calories, use 1,000 and minus 1,000 calories. And you'll get a bigger delta T, and you won't have to do so many calculations. And then just, after each delta T, lower the temperature or increase the temperature of substance S, and eventually it'll narrow the gap, and you just keep doing that until the gap is down to 0 or pretty close to 0, and then you'll have the equilibrium temperature. So map out that strategy where you basically figure out a chain or a specific number. I mean, you can do it by table. Just make a big table, calorie by calorie, or 1,000 calories by 1,000 calories, or whatever you want to do. And just work your table. And the bottom of the table is substance S's temperature, and the top of the table is substance H's temperature. And, so you're dipping substance H, and you're increasing the temperature of substance S, and eventually they come to the same temperature, kind of in the middle of your table, and ding, that's your equilibrium temperature. So yeah, you can do that. Now, I want to show you a demonstration. Hector, could you come to the front and videotape or video record my 2 excellent TAs doing a very cool demonstration of standing waves. I'm going to turn the light up. I'm going to keep the podcast going, so this will record into the podcast. And yeah, I guess you can do it over there. And what they're going to do is wait till they, Hector, do you want to be the oscillator, Caroline? In other words, do you want to? Okay, and Darian, hold it steady at your end, and maybe stretch out a little bit so that you have plenty of tension. Okay, and that'll make it a little bit easier. Okay, get me the fundamental mode. Okay, now look at what they've got going there. Go ahead and film that, Hector. That is what we call the fundamental mode of oscillation for this oscillating system. A coil spring set to the distance between these two individuals. Now don't take any steps forward or back, either of you. All right? Thank you. Good. Cut. Okay, now I want you to, and I'll tell you to start recording again in just a second. See if you can find the first excited state.
I need to go back a little bit.
Seriously? Okay. You're recording sideways this time. Good. Okay, see if you can get the first excited state. It's tricky, isn't it? The first excited state is, there we go. Is that it? That's it. Now she's oscillating. She's got a bump on the left and a dip on the right, or a dip on the left and a bump on the right. Go ahead and sketch that into your notes. Hector, you can videotape that for a second. That, my wonderful students, is a standing wave, and it is in the first excited state. The first one you saw was the fundamental mode. This is the first excited state in our parlance. And an electrical engineer might call it something different. Okay, go ahead and cut. We're going to try to get another excited state, the second excited state. And Logan, what you're going to see when they get to the second, did you cut? Okay. When we get to the second excited state, we're going to be looking for an oscillation mode in which the spring looks like, and can you guys move forward just a little bit so that everybody over here can see? Did you guys see what was happening? Okay. All right. And Caroline, can you move up the aisle just a little bit? All right. Good. All right. Now, in the second excited state, we're going to look for a bump left and right and a dip in the middle, or a dip left and right and a bump in the middle. It's going to oscillate between those two configurations, if Caroline can do it. And if she can't do it, I'll have to jump in and help out. Ready? Higher frequency. Okay, you need some more tension. Back up a little bit. First excited state, faster. No. Do it faster, but not as big oscillation. Small. There we. Hey, not bad. Ooh, Miss Caroline. She scores. 3 points. Good. Got it? Cut. All right, thanks, you guys. All right, now, you did great. Thank you. I went to grad school for 5 years to do that. She figured it out in one morning. Holy buckets. Believe it or not, what you just saw, we're going to apply to the periodic table of elements after exam 3. That's coming up. But we're going to study the wave concepts of it right now. First thing I want to mention to you is that I created a new page in web courses for simulations. It's down here. There's the home page. Galileo's looking at you and whatnot. And here's the item J on the list of pages, simulations. And when you click on that, it'll take you to a page that looks like this. And there's 2 simulations in there now, not just one. And they're related to waves. And on the second one, you can click to run it, and you can fool around with it and get standing waves. It's kind of nice. I was messing around with it this morning at home. Some of the simulations in this website are really, really cool. And matter of fact, if you want to do some unorthodox but helpful studying for the final, go straight to the link up here at the top. That's their simulation website. And you can look up any concept that we've talked about, and a lot of times you'll find a simulation for that physics concept. Whether it's acceleration or or waves or anything else. Anyways, I want you to take a look at those if you can. And it requires a little bit of Java, some of them. So if you don't have Java, it'll ask you to download Java and stuff like that. But hopefully, some of them just require a web browser. So see what you can do. All right. Now, I want to take a closer look at standing waves. And to do that, I'm going to ask you a public opinion survey with your clicker. So this is another one. And this one, actually, it has a typo in it. And you'll see it in just a second. Here we go. This question refers to Darian and Nisha. Nisha was our TA last semester, but Caroline is the one who did it this morning. Okay, so here's a snapshot of Caroline and Darian. And this is what you saw for the fundamental mode. All right. So the distance, remember I told them, don't change your distance, don't back up or move forward. That distance was about 15 feet, I imagine about 5 meters. What was that distance? Half a wavelength, a full wavelength, or 2 wavelengths? Go ahead and vote. And think about what a wave looks like. And what wavelength means. 20 seconds. That's right. That's a full wave. So what do we got here? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got. Uh-oh. We got some splaining to do. All right, now a bunch of you voted for lambda over 2, half a wavelength. Go ahead and jot down those vocabulary terms. Half a wavelength, lambda over 2. Full wavelength, lambda. Double wavelength or 2 wavelengths, 2 lambda. All right. Some of you voted for each of those. And the correct answer is A, half a wavelength. Now, so go ahead and circle that. And what I want you to think about is that as I noticed a student demonstrating up here in the 4th row, the student went like this with her hand. She went like this. And she was talking with her friend. She went, she bumped her friend in the elbow and it went like this. Okay? And that's a wave. A full wave is a one bump followed by a symmetrically sized dip. And then another bump and then another dip. So this is half of a full wave. So this is lambda over 2. Students, the physical distance that we set, I can't overemphasize the importance of this. The physical distance that Darian and Caroline set controlled the wavelength of the wave that they produced. They could produce an exact half wave at that frequency. So let me repeat that. The distance that they set by their human decision, their human judgment, they put their feet in a particular pair of locations, and then they start the slinky moving. And they get the fundamental mode. And the other modes. Once they've set that distance, only one fundamental mode, half wavelength, is possible for that spatial configuration with that slinky. Now, if you use a different slinky, a different spring, Or if you know what you could use a lot of times, if you have a long metal rod, you can get that thing to vibrate, but it's not as visible as the spring. But you can get all kinds of things. But once you set the distance of the endpoints, metal rod, organ pipe, yeah, organ pipe, flute, trumpet, violin string, piano string, guitar string. Once you set those distances and you choose your spring or your guitar string or your piano wire, only one frequency will be generated as the fundamental. Only one frequency, double the frequency, will be generated as the first excited state. And that is why when you hit on an 88-string guitar, otherwise known as a piano, when you hit one key, you get one note. Now, if you have a fancy frequency analyzer, like on stereos, you crank up the bass, you decrease the treble, or whatever you want to do. If you have a frequency analyzer, when you hit a single key on a piano, you're getting several different frequencies. They're all multiples of each other. One fundamental and then a bunch of the what they call the higher harmonics. That's standing waves for sound waves, generated by standing waves in a piano wire. And what we're going to see, my wonderful students, here's the bottom line of this little question. We're going to see standing waves control the destiny of the periodic table. The entire periodic table of elements can be understood in terms of standing waves. So what you just saw, you're going to apply to the periodic table. All right, let's keep going. The general effect that you just saw is called interference of waves. And basically, what Caroline was doing, she was a source of waves, and then because Darien was holding it steady, the waves were hitting Darien's hand, May, and then they were reflecting back towards Caroline. So as if there were two sources. The spring was operating as if Darien was a source of waves, same as Caroline, even though physically only Caroline was doing anything. All right? And therefore there were two sets of waves coming at each other. So when you have two sources of waves, you have, and if the waves move out independently, at certain points, you're going to have wave crests meeting. And if you were out in the middle of the ocean, those wave crests, where they meet for just an instant, that's going to be a rogue wave. The kind that will tip over a big ocean liner or come close to tipping it over, stuff like that. At other points out in the ocean, you may get two troughs. Between the crest of every ocean wave, there's a trough. Okay, and if the two troughs meet, whoa, you've got an extra deep hole in the ocean. And man, oh man, if you're out there, and I don't care how big of a cruise boat or aircraft carrier you are on, if you come to a rogue wave and you ride up on that rogue wave, I'll tell you what, you're going to lose your lunch over the side, because you're going to feel like puking. When you look down, especially when you look down into that trough, oh my goodness, you're going to be looking way down into Davy Jones' locker. All right. Now, the fancy name for these phenomena, extra deep trough, extra tall crest, is constructive interference. The two waves interact. And where they interact and produce a tall crest or a really, really deep trough, that's considered constructive interference. Right? There's a second kind of interference. And that is the constructive interference happens at certain points, at certain times. Okay, so you have to locate the position and the time to know whether it's going to be constructive. The other possibility is a crest meeting a trough at some point in time. And so when you have that, you've got flat water, no wave. And that is called destructive interference. So if you're out there in the ocean at any instant of time, you're going to have locations that have destructive, alternating with locations that have constructive interference. So destructive, constructive, destructive, constructive, destructive, constructive. It just depends on the shape, the timing, and the velocity of the waves, how fast they're moving, where they're moving, and what their amplitude is, what their wavelength is, what their frequency is. All right? And here's a couple pictures I want to go through with you. All right? Now, if you think of a wave out in the ocean, okay, here's a wave coming from the Western Atlantic. So let's say that this is a wave that was generated by a storm off the coast of Nova Scotia. And then let's say that this one, B, is heading to the left from right to left, so it's going east. So let's say that this is in the Eastern Atlantic, and it formed from a storm off the coast of the Cape Verde Islands, off the coast of West Africa. Now, somewhere in the middle of the Atlantic, down here, the two meet, and you symbolize that by expressing it, the waveform at that location at that time, as A plus B. All right? That is a way to express symbolically that those two waves are in phase and are interfering constructively. Okay, the fancy term that a physicist or an engineer or a computer scientist would use is in phase. And there's a lot of trig behind that particular word, but for us, you're getting crest to crest or trough to trough. Now, this is two crests, all right? And we can generate these in the ocean. We can generate them in canals and stuff. Two crests like this motating across the ocean. Yeah, we can do that. It's not easy, but we can do it. And so this is kind of an idealized picture. Now, what happens after that? What happens to those two? What happens to wave A? What happens to wave B? Right here in the middle, we get a super big rogue wave. So you're up there on top in your cruise boat and you're puking your guts out over the side and thinking, oh, why did I go on this cruise? This is no fun. But then suddenly, you're back to regular sea level because you're still right here. You haven't really moved much, but the waves have moved. Wave B keeps heading west, and wave A keeps heading right, or to the east. You know, this wave A is heading for the coast of West Africa. So if you're in Morocco or something, you're going to go surfing with this wave, wave A. If you're over there in Nova Scotia in a wetsuit, you're going to go surfing with wave B, because eventually it's going to get over there. All right? So just for a moment, you have constructive interference, but then they don't bounce off each other, they pass through each other. And that's why we say for waves, a wave transports momentum and energy, but it shows up as a change in the sea level, basically, a rise in the sea level, a bump in the ocean. But it doesn't necessarily translate the atoms or the molecules of H2O from the coast of West Africa straight over to Nova Scotia. Waves don't really do that. But the energy is transported through every gallon of H2O molecules between West Africa and Nova Scotia. And the other way around. For wave A from Nova Scotia all the way down to West Africa. Yeah. The energy is moving. It's moving through the molecules, but in itself, it does not move the molecules with it. So now, here's a case of destructive interference. So here's my second example. Now, this is a crest meeting a trough. All right? And here's a crest coming from Nova Scotia, again. And here's a trough. And by the way, when you have a big tsunami in the ocean, a lot of times it's because there's a big block of the ocean floor that suddenly rises up or suddenly drops down or does both. It rises and then dips back downward. And when that occurs, you get dips in the ocean like this. And then they propagate and cause a lot of damage and everything like that. Anyways, where these two interact, A plus B, here's their interaction. But because they're out of phase, they're 180 degrees out of phase, we would say it. They're backwards relative to each other. One's up, one's down. You get flat water, you get zero amplitude, but only for that moment in time at that location. Okay, so if you have a different location, Caitlin, Widener, you might not see flat water, but at this moment in time, at this location, yeah, flat water. All right, and then they keep going. All right? Wave B from West Africa, that dip just dips off to the northeast, heading for Nova Scotia. The land of salmon and lobsters. I guess they get lobsters everywhere. And then wave A says, okay, I'm going to go get some lobsters down off the coast of Senegal and see if they taste as good as the ones from Canada. All right. So, side note: this is a one-dimensional wave picture, left versus right, and in real life, it's actually a four-dimensional process. Why do I say it's four-dimensional? Well, the waves are spread out over the entire ocean, and they're above. The crest is above sea level. The trough is below sea level. So you have altitude. You have north and south, east and west. And then you have time. That's the fourth dimension. So a wave phenomenon is always four-dimensional. It's essentially four-dimensional. And it's hard to understand it unless you work, as Einstein admonished us to work in four dimensions. So a standing wave. Let's get back to our demonstration. A standing wave is actually a set of identical waves that Caroline creates, of which she is the source, and they just keep ricocheting back and forth, and if she puts them out at the right frequency, they'll start back, they'll bounce off Darien at exactly the time she starts up a new one. And when that occurs, you get a standing wave, either the fundamental mode or the first excited state or the second excited or any of the other ones. I've gotten it up to the third excited state before. It's tricky. It's really hard. But you could do it. Now let me pause for questions. Yes. They're both, in both examples, they're going in opposite directions. And at least they're starting, A is starting over here on the left, and B is starting on the right, and they're moving. Because what we're trying to do with those two kind of simple idealizations is think about the interaction. So they're heading initially toward each other. They interact to get a big trough or flat water, and then they keep going past each other. Right? So eventually but their velocity stays the same. All right? Another question. Okay, so you guys are all geniuses on that stuff. All right, let me slide over here to the computer display for a minute. I'm going to play you a YouTube if we still have it. Actually, I believe we do. Okay, I want you to listen to this. This is a train video up in Amsterdam, New York. And I've got the sound turned on, and I want you to listen to it. And I want you to listen to the train whistle, or its horn. Did you hear that? What happened to the train horn? What do you think? The pitch change. Did you hear that? Let's try it again. Listen for the pitch change. Sound waves. Have you ever heard that? Have you ever heard ambulances or fire trucks do that? Police trucks? Sometimes you hear it. I love trains, so I just, And if you, on this one, let me go back to. If you, all you got to do is type in rail fanning, and the guys that love trains and they make films of them cruising through are called rail fans. And just type in the word rail fanning, and you'll get tons of. See, look at this, rail fanning 2016. And if you listen to these, you'll sometimes hear here's Amtrak. So nice guys. You'll hear a lot of nerdy guys too. It's kind of amusing. But anyways, a lot of times if you listen, fast forward through all that stuff, but then a lot of times when it's just the train going by, you'll hear the Doppler shift. Okay? And that's what that's called, the Doppler shift. The reason I'm giving you an example of that is because that is how nobody in this room, hopefully, I know you're all good boys and girls and you never break the speed law or get tickets, but there are people that have, including Dr. B, and this is how they get you. With a speed gun that uses radar, not sound waves, but a radar gun that detects change in frequency of the radar. It's something called beats. And beats is a constructive and destructive interference combo that occurs when you have two sources that interfere with each other and they're slightly different frequencies. Right? Did we do the resonance demonstration in here the first day? Did we do the tuning fork on the first day? Okay, the tuning fork is, and we did the beats phenomenon with that. Um, this is what it's all about. So let's get down to beats. And basically, if the if you have two sources of waves that are slightly out of frequency, slightly out of wavelength, you'll get a big constructive interference, a rogue wave up here, then some pretty flat water here in the middle, and then another rogue wave coming by. And it's because the waves interfere, but not quite in synchronization. All right, so let's take a look at this. Now, try to draw a sketch of these. And I took a lot of time getting these sketches to do what I wanted. The red and the black waves are slightly different frequencies and wavelengths. All right, now let's determine the equilibrium position or sea level for both of these waves. Okay, so here's equilibrium position. So I have an amplitude variation for the black one and a similar size variation or amplitude for the red one. The red one goes above and below the equilibrium periodically. That makes it, and it's moving. This is a snapshot. And let's say that it's moving. Go ahead and write down the speed of propagation is 80 meters per second. Now that is really slow for any kind of a wave. Sound waves go much faster, about 4.5 times faster than that. About 300 and something meters per second for sound waves. But this is a good round number. This is kind of an idealized example. All right, so I have speed of 80. And I set up the top one to have a frequency of 106.7 hertz. So it's pretty low frequency. That would be a bass that you would feel in your bones. And frequency F2 is a little bit bigger. Also a bass that you would hear down in your bones. And let's say that in this hypothetical system, you have one source, the black waves, and another source, the red waves. And if you combine them, this is actually what the combined waveform looks like. Try to draw this, the blue waveform. This, the diagram I just showed you from an old textbook is not very accurate. This one is. This is your flat water here in the middle. All right? So this blue curve is the sum of the two waves, SUM. Right? So draw a bunch of squiggles here, big good ones, and then kind of diminishing, so you have basically flat water here, and then expanding again so that over at this location, at this point in time, you have a little bit more amplitude. Now, students, the more amplitude you have, the louder. Let me repeat that. For sound waves, the more amplitude, the louder. And for sound waves, the amplitude is the variation away from atmospheric pressure. You know, sound wave is a variation in atmospheric pressure, slightly high, slightly low, oscillating from the speakers to your ears. Okay? So this is really big amplitude. So this would be loud. Okay? If you put the two sources together, the red and the black, this is what you'd actually hear. Right? So this would be loud over here. This would be faint right in here if these were sound waves. All right? And then you'd have another loud. So when we call this beats, what we mean is, just like that first day in lecture, you know, we heard the sound wave, it kind of faded in and out. Okay? And these things are moving from point A to point B, so you get a loud followed by a faint, followed by a loud, followed by a faint. And that's how that beat phenomena kind of faded in and out. Kind of sounded cool, actually, when we got it right. So the beat frequency, the frequency at which it fades in and out, is depends on the frequency of the two sources. So it's basically the difference in the two frequencies. So the beat frequency is big minus little. And they've got to be pretty close. If they're too big, if there's too big of a difference, you're not really going to hear it. Okay, and remember on the tuning fork, the amount of beats that we heard, or the clarity of the beats we heard, depended on where I put that little tuning fork, or that little clip on the other tuning fork. The same thing here. So for this one, the difference in the frequencies is 12.8, and that's a really low bass. You would feel that one in your bones as well. So the beat frequency 12.8 actually tells you something about your two sources. Let me repeat that. The beat frequency tells you something about your two sources. Let me repeat that a third time. The beat frequency tells you something about the two sources, the red and the black in this case. Right? And because it does tell you that, you can deduce something. If you see this beat frequency, you can see it and figure out something about, here's the wavelengths, by the way. Lambda 1 is 0.75. Lambda 2 is 0.67 meters. You can figure out, and here's the wavelength of the beats, 6.25. So from loud here to loud over here is 6.25 meters. And these are good, accurate numbers. I made this really precise. Okay, so here's the beat wavelength diagram, and this is what you'd hear. Okay, you'd hear loud, faint, loud, faint, loud. And the distance, Haley, between loud and faint is lambda sub. So if you know the beat frequency and the speed of propagation 80, V equals lambda F, you can figure out lambda. All right, now let's talk in detail about how cops nab speeders using radar. All right. The radar gun has a little computer on board, and it measures the beat frequency. Now, why does it have a beat frequency, or why does it measure it? Why does that radar gun, if you look back at the picture, look at this. He's got two little windows here. See these? All right. This is send, and this lower one is receive. All right. And he compares what he sends to what bounces off your car and comes back to his receiving device. Okay. Now, the Doppler effect, that change in pitch. If everybody is stationary, then a sound at 113.2 hertz will sound the same to everybody. But if the source moves toward you, like this train, and here's the actual YouTube address for it if you care to write it down. If the source moves toward you, the frequency increases. So as long as that train was moving toward us, we heard a relatively high pitch. Now, if it were parked right next to us, the frequency that we would hear, or the pitch that we would hear, if we were in the cab with the engineer, or if the train was parked in the freight yard and we were listening to it, the guy hit the horn, it would sound a little bit lower than what we heard on approach. Similarly, if the source moves away from you after it passes by the cameraman in the video, you have a lower pitch, and that is relative to the source that you would hear, the pitch that you would hear if you were either in the cab with the engineer riding along, or if the train itself was stopped and you were, alongside the track listening to the horn. Now, the radar gun also observes a frequency change from reflected radar. Now, for the video, we hear that change in the frequency basically because we remember the frequency. It's like a change that we can appreciate or measure because of what we remember. So we remember the first early sound as it's coming toward us, and then we notice it when it dips to a lower frequency after it passes by. The radar gun has an internal memory, I guess. It sends out a certain frequency of radar, so many gigahertz. And then what happens is if your car, and I want you to add this to your notes carefully, if your car is moving toward the police officer, the reflected radar waves have a larger frequency, a higher pitch, therefore a shorter wavelength. All right? So make a note of it. And this would be in addition to number 2. If you are moving toward the policeman, the radar waves that bounce off your car come back to him, higher frequency, shorter wavelength. All right? That's if you're going toward him. And because he can measure that, he'll pick up the beats. He can figure out how fast you're going. If you're moving away from the police officer, you're not going to outrun the radar. It'll bounce off you and come back to him. It goes at the speed of light, so it's pretty fast. But if you're moving away from him, it's like number 3 down here. All right? Lower pitch for sound waves means smaller frequency for the radar. So when you're moving away from the police officer, the radar comes back to him at a lower frequency. Smaller frequency, bigger wavelength. Right? So number 3, radar-wise, smaller frequency, bigger wavelength. And the police officer's radar gun, it's got a little computer on board. It'll be able to measure that. And because it can measure it, it can compute the beat frequency. Right? So here's how they nab you. Go ahead and write down this fancy equation from the theory of relativity. The quotient of what he gets in return divided by what he sends out, so this is send and receive here. This is the frequency quotient. It's equal to this big square root. Now, we're not going to calculate this, but this, I want you to see it and realize that the speed of your car is right here, v. And it's also down here in the denominator. All right? Now, if your car has got a positive v, that means it's moving away from him. Right? If it has a negative v, it's moving towards him. Right? He'll be able to pick up. And so what they do is they solve this equation, and so you measure the return frequency from the moving car, and the computer on board his detector already knows the factory setting, so it's set out to 1.21 gigahertz or something like that. And it knows the speed of light. Go ahead and write down all 8 digits, or what is that? That's 10 digits, I guess. 3, 6, that's 9 digits of the speed of light. It knows that to fairly well. And that allows the computer to solve for V. Now, I could walk you through solving for V. It's not that bodacious, but for us, it's not important to calculate V as to know that, yeah, you can get it. Okay, so for instance, if the frequency of the gun is 100 gigahertz, for instance, then the lambda is going to be 3 millimeters, 0.003 meters. And millimeters is a radar wavelength. They have millimeter band radars all over the military has tons of them. Okay, I don't know what the cops actually use, but this is a typical radar frequency. Now, if you measure, go ahead and write down this big number. Let's say that the return frequency that comes back from your car, no, not your car, but one of your enemies, because you're a good law-abiding citizen. Everybody here's a good law-abiding citizen. But one of your enemies, like the Dallas Cowboys, they're my enemies, eternal enemies. Anyway, so Jerry Jones's car repeats and it sends back a reflected signal just a little bit higher than 100 gigs. I see somebody in the back squinting their eye trying to get all the zeros right. Yeah, let's count them here. 1, 0, 0, 0, 0, 0, 0, 6 zeros, and a 26685.132. So let's say that that's the frequency it comes back. Nice. The B frequency is 26685.132 hertz. And guess what that corresponds to, my wonderful students? Very small fraction of the speed of light, but yeah, 89.5 miles per hour. Jerry Jones is busted. And here's the thing about it. These radar guns, boy, they're hard to beat. They are hard to beat. Because this is 267 parts per billion. So they have pretty good precision on these measurements. I mean, unless he's like pointing it at the clouds or something like that, he's going to, nab you if you're speeding. So don't worry about on the exam that you're going to have to calculate with this formula. Do worry about heat, melt, heat, though. But yeah, if we can measure beats, we can give you a speeding ticket. So keep that in mind next time you're tempted to drive like a maniac. Out there on University at 3:30 in the afternoon. Did you ever notice that? Out there on University heading west, like 3, 4 o'clock, 5 o'clock, there's maniacs everywhere. Especially maniacs on motorcycles. I saw this guy driving between cars that were about this far apart. Oh my goodness. I just see something like that and I kind of like this guy here. Now here's a sneak preview. We're heading for, I believe it's chapter 7 in our book. Electrons and atoms, electromagnetic field. What do you notice unusual about this photograph? Guy's got a pickup truck full of rocks. What has he got a chainsaw for? It's a little. I found. Those are big chunks. This is from up in Canada, a place where you can get raw jade. Here's our big study target, the periodic table. So we're going to start working into that after exam 3. So just keep that in mind. Homework 16. I'm going to give you a little study homework tonight, and look at the simulations, and also do your study groups. I'll see you on Thursday for exam 3. You are dismissed. Oh, special study group leaders, all of you come up here for last minute instructions.